objective of this lab is the representation of discrete time digital signals into frequency domain via fast Fourier transform, resolution of spectrum, computation of magnitude, phase and power spectrum, spectrum leaking, and avoid spectrum leaking. The task 1, write a MATLAB program to validate the above given decimation. Program first divide the given signal into even and odd samples, calculate DFT for even and odd samples separately, and then merge them both by using the formula which is given, where G of k is the DFT of even part and H of k is the DFT of odd part. And this is the code in which the signal is given, which is named as 1 2 3 4 5 6 7 8. Divide the given signal into even and odd samples. Even sample is equals to signal 2:2 end, and odd sample is equals to signal 1:2 end. Calculate the length of the signal, which can be derived as n is equals to length signal. Now calculate the DFT for even and odd parts separately. GE is for the even part and HO is for the odd parts. Merge both even and odd part using the formula k is equals to 0:n divided by 2 minus 1, and xk is equals to even part plus exponential, and this is the formula to merge the even and odd parts DFT. Now display the result, and the resulting output is this. In task number 2, check the above program for the given signals. Now the signals is given from x1 to x8. Observe and find any symmetry in function in frequency representation. Also match the calculated DFTs with standard function in MATLAB featuring fast Fourier transform. Assign a function with assign a function x of k which is equals to validate decimation signal. Now divide the signal into even and odd samples. Calculate the length of the signal. Calculate the DFT for even and odd parts separately, which is GE is equals to fast Fourier transform even samples and HO is equals to fast Fourier transform odd samples. Merge both even and odd DFTs using the formula. Now the signal is given in the task. Iterate through each signal using the for loop. Calculate DFT using provided functions. Xk is equals to validate decimation signal. Display the DFT using provided functions. Calculate DFT using standard MATLAB functions. Now check the symmetry in frequency representation, and the resulting output is this. For x1 3, the DFT using provided function 4, DFT using FFT 4 minus 2. The frequency representation is symmetric. For signal x2, the frequency representation is not symmetric, and so on up to x8. In task number 3, check the program in task 1 for given signals given below and compare it with standard functions x and y. Now define the validate decimation function. Divide the signal into even and odd samples. Calculate the length of the signal and calculate the even and odd samples separately for DFT. Merge both even and odd samples DFT using the formula. Now signal is given in the task number 3, which is x is equals to 1 2 1 1 0 2 3 and y is given as this. Calculate DFT using provided functions for signal x. Display is equals to signal x, xk is equals to validate decimation x, and display the DFT using provided function. Calculate DFT using standard MATLAB function and display the result. Calculate DFT using provided MATLAB function for signal y. Display the result. Calculate DFT for standard MATLAB functions for signal y. The resulting output is this. For the signal x, DFT using provided function is given below, and for the signal of y, the function is given. In task number 4, we can further subdivide the above decimation up to 2 samples and calculate the DFT of 2 samples. Then 2 samples DFT added to form 4 sample DFT and 4 samples DFT to form 8 samples. So this 2-point decimation is called radix 2 fast Fourier transform. Write a program my fast Fourier transform that transform a given signal into its frequency representation using radix 2 algorithm. So define the my fast Fourier transform function. Check if the length of the signal is a power of 2, n is equals to length x, and by case if length is 1, return the signal itself. using the return function. Now split the signal into even and odd parts. Compute the FFT of the signal and even and odd parts recursively. Now combine the FFTs of even and odd parts. The output is given. In task number 5, calculate the fast Fourier transform using your own function from task 4 and compare it with standard functions using DFT for the calculating following signals. First of all, define the my fast Fourier transform function from the task number 4, which is function x is equals to my fast Fourier transform x. Now check if the length of the signal is a power of 2. By case, if the length is 1, return the signal itself. Using the return function, now split the signal into even and odd parts and compute the FFT of the even and odd parts. Combine the FFT of even and odd parts, and the result of task 5 is given. For signal W, for signal X, for signal Y, and for signal Z. So this is the lab